software, and those primitives give you the language you can speak to the hardware, what sort of software runs well, what runs poorly, and it really, the shape of performance and flexibility and generality and efficiency that you get. Okay, so traditionally, for decades, this was actually a pretty stable thing. So we talked about instruction set architectures, Intel's x86, ARM being a RISC instruction set, and then of course there's the system architecture, the interrupt model, your storage architecture, your networking architecture. But really people talked about the instruction set because that's the software interface down to the hardware. And then of course networking and storage. And so I show you up there kind of a conventional, PC design, although this is a server design, 2 CPU sockets. And this model was very stable for a long time. You had a disk, you had some processing, you had some memory, you had networking and storage. And this is it. This is what you get. And then in PCs, of course, people started putting in GPUs for graphics. So this got a little bit richer. But it's been pretty stable for a long time. And now all of that is cracking apart. And that's what's so exciting. And so there's a lot of disruptions happening now at the same time, which makes this a crazy time, both in the research field and industry. I don't have time to go through them all. But some of the big ones are, we're connecting everything via the networks. So we're getting tons of information streaming in. This is, people as endpoints, cars, sensors. So you can digitize agriculture. You can digitize energy management, environmental studies. The data mining we're able to do is massive. So that this everything being networked has providing floods of data. You get telemetry out of an engine as it's going, a jet engine as it's going, for example. And then a couple other things have happened. We have machine learning has gotten much better. So we're able to now learn things about those data that we weren't able to learn before. We've gotten much faster compute, but this also intersects with the end of Moore's law and the fact that computing is not going to get better without changing the architectures the way it has in the past. And then the last thing that's happened is this cloud computing thing has happened, where you can rent computers in the cloud. And while this, when I heard this years ago, I thought it was a hype term, but it turns out that it's actually a big economic disruptor, and it's really a disruptor of the information technology industry. But it's allowing us to build things and make investments at scale that we weren't able to before. And so I'll talk a little bit about that too. Okay, so back in 2013, I gave a lecture that actually one of you all emailed me about, and it was looking forward at the end of Moore's law, which we were trying to predict and to figure out what should our strategy be, because if at a company at Microsoft, we're one of the 2 big cloud computing providers, and there's there are a couple other candidates that I think are maybe viable in the long term in the cloud industry as well. So we're provisioning tens of billions of dollars of infrastructure around the world. Billions and billions of dollars annually. And if there's a big change in silicon architectures, we need to know about it, and we need to predict it and adjust. So we were spending a lot of time looking forward, saying, what are the new paradigms going to be? And I just wanted to give this as a broad overview, but I'm going to dig into 2. So obviously, silicon architectures are going to change, and that's what most of my talk is about. People talked about are now talking about specialized computing, meaning we're getting away from that x86 or ARM-based CPU model when we need extra compute. The silicon has to get more efficient than it's been in the past. So this is a big transformation that's happening. This is where I'll focus the bulk of the talk. Then a second paradigm for computing is neural. And we have this existence proof of this amazing thing in our heads that burns 20 watts and does things that computers aren't capable of. So obviously, there's been a lot of investment in that, and we're making lots of progress, although we're diverging. We have silicon deep learning or neural architectures, and then we have biological architectures, neural architectures, and they're not actually converging. They're not the same. We're building something else. Okay? But there's an existence proof that can maybe give us some inspiration or guidance, and I think eventually we're going to have to cut over and be more like biology. Sorry, STDP is spike timing dependent plasticity, and I should have said that. And right now in traditional deep learning, what we're doing is just lots of matrix vector multiply, or matrix multiply if you're training. It's basically linear algebra, and then you do back propagation, stochastic gradient descent, following the chain rule to minimize errors and train the networks. Everything fires all the time. Your brain actually works very differently, and we talked about this today with some of the students. You have a neuron in your brain, and it's really quiescent, and it's maybe connected to 10,000 or so upstream neurons, and pulses are arriving, and only if the pulses aggregate to above a certain threshold does your neuron fire. And it depends on the timing of the arrivals of those pulses. So biological networks encode huge amounts of information with small variations in timing. And the time can be adjusted by the synapses and the dendrites. And so your brain is capable of doing computation in a very small number of neurons that we can't do even with large networks today. And we don't understand, we're learning more and more. We don't really understand that computing paradigm. And it's so efficient and so beautiful. I wish we did, so we could go and chase after it, right? We're building these amazingly efficient silicon deep learning architectures, and our brains are still 100,000 times more efficient. So it's actually very frustrating. And people that have been trying to build spiking networks based on time have largely failed. They call it neuromorphic architectures, inspired by biology, but they're not able to learn anywhere near the accuracy that we are with our sort of brute force digital deep networks. And then our brains are a big jump beyond that. Right? So that area is just taking baby steps. So I think eventually we're going to have to transition over, but we don't understand the model. At least I haven't seen anybody claim they understand the model. There may be people that do, and they're holding it back for a big announcement. The biological paradigm is another one. People are starting to program biology, understand gene expression to protein pathways to gene expression, mapping that out. It's more of a statistical thing with lots of chemicals and DNA combining in different forms and protein interactions. But it is a compute paradigm that we're starting to map out and be able to understand and express languages for. And then we're also leveraging DNA, as I'll show in a little while, to do more traditional sorts of computing. So that's another paradigm that we can run in, but that's very, very early days. And then, of course, people talk about quantum quite a bit, and quantum is making a lot of progress. I think there's a misconception that quantum will replace traditional computing stacks. That's not at all true. I think quantum will enable new algorithms, whether it's quantum chromodynamics or molecular simulation. Certainly prime factorization is well understood. So we'll solve some really exciting problems that can't be solved with conventional computing with quantum, but it's not going to replace the existing stack. So these are all sort of very different types of computation that will accomplish different things. And so these are sort of at least when I thought about it back in 2013, seemed to be the four. And the good news is, since then, we've made a lot of progress on all of them, but I only have time to talk about really one or two of them today. And then on the quantum, there's a bunch of different approaches to try to make that work. Ion traps, where you're trying to trap a subatomic particle and then do compute on it. And then Microsoft has an approach called topological qubits, which is very, very hard. They're very hard to build. You have to be down at, I think the number is 4 millikelvin or 10 millikelvin, somewhere in the single-digit millikelvin range above absolute zero, a few thousandths of a degree above absolute zero. But then you get subatomic particles forming that were only theoretical until a few years ago, but have since been proven, and those tend to be very stable. So if we can form them, then we can have stable things that we can then build on top of. But they're hard to form. So there's multiple approaches, and people are spending huge amounts of money on different approaches to this, and they're big bets. But that's going to be an important new paradigm as well. Okay, so when I talk about the cloud and all this amazing machine learning and big data, all these things we're able to learn, I'll dig more into that in a moment. But what's driving this? And it's really three things. I said some of it already. So one is capability. We're able to do a lot more compute. That's one of the things that's driven this explosion in deep learning. Yeah, the way to think about deep learning is the more labeled data, meaning data with the answer, you throw at it to train, the better they tend to get. And the more compute you throw at it, the better they tend to get. So you need a lot of data, which all the sensors and networking of everything has provided. You need a lot of compute. GPUs in particular have driven a lot of that explosion in compute capability. These are graphics processor units, for those of you who aren't familiar, the things that render graphics on your screen. And then, of course, you've got to have the distribution points. And now people have mobile phones. They can consume the services based on these. Industry can use them. it's really exciting what that's been able to do. And deep learning is particularly interesting. And it's sort of at the top of the hype cycle. There's a ton of hype. It's like a gold rush. Everyone's rushing into it, sadly, including us. Don't work in popular areas is a good research rule. But what's happened is deep learning, when it was seriously started being looked at, around 2009 were some of the early breakthroughs. What happened is it started to march through all these different areas that each had their own proprietary set of algorithms that had been tuned over decades. So, speech processing and vision and natural language translation from one language to another all had completely distinct sets of algorithms, and deep learning kind of washed through them. And now the deep networks that do those aren't all the same, but they're variations on a theme. And so they just seem to be very general, and they're being more and more general, which is really exciting. We're starting to encode broad knowledge in deep networks. To get back to the example, the more data you throw at it, the better they get. We had in MSR, we had a model that was really good at doing taking audio and recognizing what English words were being spoken in that audio. And then we decided to build a bigger model, and we trained it both on English and French. So we trained a model that could both recognize English sentences and French sentences and translate them, produce the English words or the French words. And the model had to be a bunch bigger, so more compute, more data to train it. But it was able to do both, which is pretty impressive. Humans, it takes a long time to learn a language. But the really weird thing was, when we added all the French data, the English model got better, right? And because there's some sounds in French that aren't as common, and they're sort of completing the features in the network. And then if you add Chinese, the English and the French get better still. So there's just something very fundamental about building networks that are big enough that they have lots of little tiny features that make your translation better. And that was really what opened my eyes. That's a very powerful result. Okay, and then the IT industry, I'll talk about that in a moment. And then the other thing that's driving the need for new models of computation, getting away from that CPU-based box that I showed you at the beginning, is two failures. Dennard scaling, which failed around 2004, 2005. Bob Dennard from IBM, who was a legend in the field, proposed setting scaling rules on how you shrink circuits from one generation of silicon to the next. And it was, you shrink the insulator by this much, and the width of the transistor by this much, and the voltage by this much. It was a set of rules. And every time you did that shrink, the transistor got faster and lower power and smaller, and therefore cheaper. So it was sort of like magic for decades. And then that broke apart, failed in around 2004, primarily because the insulator on these transistors started to get to be too few atoms, and you couldn't scale it anymore. So you couldn't follow that scaling recipe. And then we started to see power climb up because we weren't able to drop the power consistently as we were integrating more circuits on the chip, more transistors. All right, so that led to an explosion in multi-core chips, and has really driven, it's one of these things you don't know when it's happening. And then Moore's law, which really talks about the number of transistors you can fit on a chip, actually I think failed a few years ago. It's kind of like you're a frog in boiling water. Is it active or not? So I'll show you a chart that kind of makes that case. Although I'm sure people will debate years from now about what was the exact day that it really failed, and we don't really know. Okay, but we've been on an exponential curve in the dropping of compute costs for 5 decades or more. So when that changes, that's been pretty much our whole professional lifetime. So when that changes, that's a pretty big change, and it's happening now. All right, so I'll show you a chart back from 2000. I don't remember when this was, 2010-ish, where this is a log chart, and so you can see that in green the speed of processors had been going up exponentially for decades, and the performance on software in blue, single-thread performance had been going up exponentially, and in red on the top the number of transistors had been going up exponentially. But then you see that there was also an explosion in power. It started to crank up in the late 1990s because of the clock frequencies, the speed of the chips we were pushing, and then Dennard scaling made it worse. And then so we stopped scaling the frequency in green. You can see how that levels off there, and the single-threaded performance started to level off. And as the industry said, what are we going to do? This is terrible. Like, we need to keep building something. So they started stamping out more cores, more CPU processors on the chip. and that started growing. And of course, that was a short-lived thing, and it's capped off except in some cloud markets. But you can see that the number of transistors, so the area you had to work with on a chip was still going up exponentially. And then back in 2014, I had a review with our executives at Microsoft, and we were talking about this. And so on this chart, I showed the planned silicon roadmap, 2010 all through 2022, and the tech in nanometers is the width of a transistor in nanometers, 3222, scaling exponentially down. And the transistor shows the number of transistors you can integrate on a chip of a given size in billions. So it's a lot. And then they asked me to make a prediction, and so I said, well, things are looking really hard in the orange regime, and I don't think we'll get to the red regime in any useful way. We might. And I said, I think we're going to run into the wall somewhere between 16 and 11 nanometers. Now remember that Moore's law is not about do we ever scale to smaller circuits. It's a consistent rate. Every 2 years, boom, 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 we drop the size of the transistor by about 70% and therefore double the number on a chip. So let's see where things actually ended up. So what this shows is public Intel data. And what I'm graphing here, I don't show all the process nodes, but it's the number of years on the y-axis to the next shrink of silicon. Okay, so you can see in 1990 it took 2 years to get to the next one, then 2 years, and that's been true for decades. Boom, 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 boom. There was an industry cadence that people were adhering to. And then you can see what happened in 2014. It took them an extra half year to get that out. It got harder. And then it took 3.5 years to go to 10 nanometers, which they finally got out in 2018. And at 10 nanometers, the next planned node is 7 nanometers, then 5, then 3. At 3, you're talking about 12 silicon atoms in the channel. So you're down near very, very small atomic limits, and quantum effects are already starting to crop up all over the place, leaking electrons and static power dissipation. So this is a huge challenge. So we're still, I think, going to shrink to a few more small nodes, but the performance we'll get out of them, how fast are they, how much power do they leak, how expensive are they to manufacture because the costs are going up. When we get to a point where I can buy a chip with double the number of transistors, but it's more than twice as expensive as the previous generation, maybe I should just buy 2 chips of the previous generation. So that kind of puts an end to the whole thing. So if your cost per transistor isn't dropping, then it's kind of game over due to economics. And this is all economics. Like we know how to build single atom transistors. IBM demonstrated that a while ago. Okay, but building billions of them reliably at low cost is probably not feasible at a single atom. Okay, so I just looked at this chart. I just did this morning, and I hadn't actually had a perspective on the date until I gave this talk. So I'm going to call it 2015, sort of just when that next node came out and we had already fallen half a year behind the cadence. Maybe that was a one-time bump, but then the next one was longer. So that looks fundamental, because this is just getting harder and harder with each node. All right, so I'm sure we can all, there'll be lots of debates. Is it 14? Is it 16? Kind of depends on how you define it. All right, well, this changes everything. Okay, now there's another trend. I want to talk about verticalization in the cloud. This is more of a businessy thing, and maybe not as interesting as the fundamental technical concept like Moore's law, but it matters a lot to how things are getting structured. And so, a decade and a half ago, we had a very horizontal business ecosystem, right? There were fabs that built silicon chips down at the bottom, and then Intel has fabs and built chips, and there were other chip vendors, and people like Dell and HP would build PCs. Apple built their PCs. Microsoft had the OS. Apple had their OS. Microsoft had Office. People would build apps on top of that. And then in the data centers, Intel and AMD were building the server processors. The OEMs, HP and original equipment manufacturers, HP and Dell would build the servers. People like Google and Amazon were building data centers and running services off of them. Google very quickly pivoted into building their own servers. What's happened since, though, is something very different. What we're seeing is we're building these big stovepipes now. And I think this is why you've seen industry started hoovering up a lot of people. We're building these monstrous verticals, and this is even, the major players are even moving down into silicon, which is a huge change from what has happened before. So I'm just listing some of the startups that were purchased. Apple's done it mostly at the device level. They build their own processors now. Google has built a lot of hardware, is building custom chips. Amazon bought Annapurna. which is a data center accelerator. And it's sort of an end-to-end stack, and there's pressure to move even further up and further down into server chips and client chips. So what we're seeing is the emergence of these big stovepipes, which means you can do end-to-end optimization. So you can sort of rethink the whole stack rather than being trapped by the interfaces you had at each level. And you also have the scale to invest. And so now, if I look at sort of the history of server class processors, or big iron, we used to have mainframes and vector machines, and of course these things still persist. So these didn't go away. They don't sell as many. And then DEC and mini computers and PCs came, and people were building supercomputers. Then Sun and workstations and servers and DEC workstations and laptops started to come out. People started networking the workstations together. And then people started to take the servers, and at the client, we went down to smartphones. So at the bottom, you can see that the consumer granularity is getting smaller. This is obviously a well-known trend. At the top, it's just changing. And then people are starting to build data centers of these servers and big rooms and warehouses of these. So made of lots of individual servers as opposed to big iron mainframes. But then they started to virtualize them, which means you wrote the software, and VMware pioneered this, to effectively create the view of multiple servers running on a single physical server so that you could get more efficient consolidation of software. And so that allowed you to really cost optimize your servers, and this paradigm really took off. And then Amazon said, hey, why don't we start renting some of these to customers? Because we provision so many and sometimes we don't need it all. So we'll just say, hey, you can rent a server in our cloud. And then so that is what became the cloud industry. And then, of course, we have the Internet of Things, where lots of things, tiny things, cars, smartphones, sensors, toasters, appliances, are all being put on the internet and providing a lot of data. And so when you put the cloud now, the cloud is kind of eating enterprise computing. And so it's turning into a giant thing. And I can't overemphasize how big this is from an economic disruptor perspective. So Azure, so right now there's two leaders, Microsoft and Amazon, and Google's fighting hard in third place in this cloud industry. Azure last year, it's already huge, billions of dollars of revenue. It grew 96% last year, which means it's basically doubling every year. And we expect that to continue for 3 or 4 more years. So these cloud vendors are going to eat most enterprise computing. And so all of this computation is going to be centralized in a small number of players. Then they get the economies of scale to really innovate across that vertical stack that I showed you. So now we can actually shift the computing paradigms much more quickly, so long as we can provide something useful to people. And so when you put these two things together, you actually get something very different than what we've had historically. So you end up with a number of mega data centers, hundreds of thousands of servers per data center. These are kind of big iron places, as big as many football fields put together. And then there's smaller edge data centers around them that talk to them. These are more, think of these as being in municipalities and cities connected to the big ones. And then around that, you have a bunch of customers that might have their own servers that talk to this whole big cloud thing. So think about a bunch of servers sitting in the back end of a retail store or in a factory. And then you have, of course, zillions of little units, whether they're smartphones or sensors, all plugged into this thing with secure channels talking to this big thing. And this is what's emerging out of this whole thing. And it's a hugely disruptive shift that, day to day it doesn't look that different. But when you look back how things looked 4 years ago, it's very, very different. And we're able to do many more things. And one project that MSR has been a little bit public about is called FarmBeats, which is the digitization of agriculture. Sensors, drones, pumping data to the cloud to figure out how best to actually run agriculture to maximize yield, maximize environmental conservation, minimize fertilizer, minimize water usage, all that stuff. And you can do just amazing things with it, as one example. And so then I'm showing here, this is actually a slightly dated slide, so there's been a lot more regions. But if you think about Azure, just one of the cloud vendors, which is Microsoft's cloud, we're building data centers all over the world. Those are the big ones, and then there's a lot of smaller ones. And these are connected with huge amounts of fiber optics to carry data. So this really is a global supercomputer that we're building. And then those are the big ones, and then it has all these outer shells that I showed in the previous slide. And I just want to summarize 2 quick examples of what this sort of scale allows us to do in terms of investment and innovation. So one is a project that we've talked about publicly. We haven't talked recently about its current status, but it's alive and well, not in production yet. And the idea, I talked to some people about it earlier today, is that you put data centers under the ocean surface. So these are underwater data centers. And when somebody talks about this, people sort of think that sounds crazy. Turns out that this is really great because you only have to build one type of data center. Whenever we go into Belgium or Thailand or Arizona, it's different power company, different environment, different local laws about data usage, different local laws about renewable energy, different power contracts to sign. And so every data center that we build is sort of a custom design. Here you can build one thing and you just sink it 200 feet down in the ocean, and it's the same design. You put pressurized nitrogen in the compartments so that the servers that you're running don't have oxidation. You have very few moving parts. You can use the ocean water to cool. There's just heat goes out about that far from the vessel because the carrying capacity of the ocean is so high. And then you see those fans off in the side. You can use ocean currents to actually provide the power to power those data centers. So the only thing you need is a data connection coming to the shore. About half of the world's population lives within a millisecond of coasts where these can be deployed. So this is an example of the sort of thing that you can do. And one cool thing about this, these are actually immune to Carrington events. So when a big solar flare, the Earth is in its path, everything else gets fried. These things will keep on humming. So for continuity of business, this is super interesting. And so I'm showing you our phase one here. We took a pressurized vessel, put some servers in it, sunk it into Puget Sound, was down there for quite a while, working well. Do you have a question?
Yeah, of course we can't use these data centers because all of our other devices are fried after the solar flare.
It's true. I'm not saying it would be useful, right? But there is some attraction in actually having the data still be there when we bring everything else back up. Yeah. And then this is a picture of one of the large Geier turbines that the currents will turn and provide power to the data center. OK, so I'll give you. Oh, go ahead.
What law controls?
I'm sorry?
What law controls? Like, suppose I had pornography on my data center. Who could stop me?
For?
The data center is in the ocean.
Yep.
On the high seas. What law is in place?
I think it's international waters. So.
There is a law of the sea.
Yeah, I don't know the detailed. I mean, I know our legal team has looked at it and they said actually it's pretty great because you're kind of independent of a lot of the national laws. Now, for our business, some countries actually require the data centers to be in their national boundaries so that the data usage laws apply to their data. And that's one reason we're building out so many different geographic distributions. So we'll still have data centers, say, within, on England, Ireland, and whatnot. This is where you would run stuff which can be independent of the laws of a governing country.
Gives the word phishing a whole new meaning.
That's, yes. To those who didn't hear, yes, it's a new type of phishing, hopefully much more benign. OK, and then a second project, and I think Professor Heckel, Reinhard Heckel, I don't know if he's here, but he did co-author this paper. He's a Rice professor. Is DNA storage. This is Karen Strauss, is a senior researcher at MSR who's been pushing in this direction. And the idea is that you take traditional digital data and you use DNA synthesis to encode the data. So you're actually synthesizing DNA chains on a synthesis chip. And then you can store the data encoded that way. And when you want to read the data back out, you want to sequence it. Why is this interesting? We're generating so much data that we actually can't possibly store it for long term with traditional technologies. So we have a major investment here. A whole data center's worth of data would fit in the dot you can see there at the end of the arrow. Actually, you can't see it because it's too small. But there's a dot there, I promise. And it's incredibly dense. So DNA storage is really interesting because based on the work that I mentioned, if you chill it 10 degrees Celsius, it'll last for 2,000 years before degrading, which is a nice feature. Just don't lose power. And it's incredibly dense. So for data that you want to store but not read a lot, it's pretty useful. And then I'll skip over the pipeline in the interest of time how we do it. OK, so all of that, the end of Moore's law, needs to drive the need for new types of architectures. We need more efficiency. The verticalization of the industry is allowing us to do more interesting things. You know, if you've got different companies building each layer, it's very hard to change the interfaces. You can, but it's a lot of work. And so the question is, what are we moving towards? And what we're betting on is something that I'm currently calling structural computing. I don't know if the name will change, but the idea is that rather than software where we compile software down to a long sequence of individual instructions, you know, add, load, multiply, what we want to do is start mapping structures down onto the silicon, which are higher level software constructs. And we're going to get efficiency this way, because actually, you know, doing an operation instruction at a time, even if you're using parallelism, is really inefficient. And I'll give you one number. So if you take an Intel chip, a last generation Intel chip, and take a floating point add instruction, it's about, from an energy perspective, it's about 0.3% efficient, meaning that about 1/300th of the energy goes into the actual circuitry doing the mathematical operation, the floating point add. And the other 99.7% is going into energy to do bookkeeping, fetch the instruction, move it around, move the data around, all the control logic, finding out who's consuming the result of that operation. So it's incredibly inefficient. The problem is it's very general, and we're able to use it and reuse old software. And we haven't really found anything yet that's easy to use that will provide much greater efficiency outside of vertical domains like graphics processing and now deep learning. Okay, so I want to talk a little bit about why we need hardware specialization. And here what I'm showing is the, and by the way, is that clock right? About 20 minutes?
We did not sign an NDA.
Yeah,
Okay.
it's fine. I'm done at 4 by that clock, is that right? Okay. Okay, so you can build custom chips for the cloud. And so if I'm going to take an algorithm, I'm going to synthesize it directly down to fixed silicon. I want it to be, that algorithm that I synthesized, to be stable for about 6 or 7 years. And because the investment to do that is pretty high, I want it to run in most of my servers. So on the y-axis, I show the percentage of servers that something might run in, 0 to 100, and then the time that that workload is stable. And if you have something up there in the green, where the green dot is, that's perfect, right? It runs everywhere, so the economics are great. It's stable for a long time, so I can actually deploy it. But my infrastructure, like my networking and storage protocols, actually change much faster than that. And there are different ones that run on different servers, although you could, you know, there's a big bunch that run on the same type. But if I look at applications, they're actually down here, right? Applications in the cloud are changing weekly or monthly. Nothing runs on more than a couple % of our servers. So it's just hard. So we said, OK, we can't go with fixed logic. So we want something that's very general, like CPUs, programmable. But we need something that's efficient, like custom silicon. So that's programmable accelerators. Well, which ones should we use? And we want this to be general across our fleet. To get started, we didn't want to try to deploy 100 different types of accelerators, you know, in each and 1% of the servers. And so what we ended up taking a bet on was FPGAs. And I'll show you, I'll define what they are in a minute, but I'll show you why they're important. So a CPU versus an FPGA as an instance of structured computing. What a CPU really is good at is it's good at taking a long list of instructions, you know, small operations, and operating on a long list of instructions operating on a very small amount of data. So the data held in my level 1 caches and my registers. Okay, so if you're using lots of data, a CPU really falls down and performs poorly. So you got a small amount of data held there, and you're just streaming instructions through that. We would call that temporal computing. So structural computing is where I fix the operations on the chip, and I stream data through. So I'm actually pinning a higher order structure on the chip, and then data is just flowing through it. So for deep learning, I might have a deep learning pipeline, and that's fixed. It's not going to change, at least for the time being. And then I'm flowing requests through it. Okay, so you're really just taking the structure, and rather just than streaming the operations through, you're pinning the operations, pinning that structure on the chip. And then individual operators can point directly to other operators. Okay, so what FPGA technology is, stands for Field Programmable Gate Array. And what it effectively allows me to do is take a hardware design that I might have designed in a hardware language like Verilog, take that, and just like I'm going to design a chip with it, instead of synthesizing it down to polygons of different material, which is how you build a custom chip, I'm synthesizing it down to bits that fit into logic tables. And so a little logic table on an FPGA can be an AND, an OR, or a NOT gate. They're actually a little bit larger, so it's richer functionality, but you get the idea. And so those can form logic gates, and then I can build circuits out of those virtual logic gates that are just little memory tables with zeros and ones in them. And so by changing the zeros and ones, I can change that logical function. And I have millions of these things all networked together. So I can take a hardware design and map it down to the chip. The great thing is I can change it later. Okay, so it's programmable. These have historically been tough to program. I'm not going to talk about that today, but we've made a ton of progress in making them much more programmable from higher level languages. So I can do a hardware design and just skip over it. I'm going to, in the interest of time, I'm going to skip over this, which is sort of the history of the deployment we did. Okay, but I want to get to what the project's name was Catapult, and what we ended up doing was taking one of these FPGA chips and putting one in all the new servers we buy at Microsoft to first order, 99%. And so right now we have a very, very large number, minimum hundreds of thousands deployed. And what we did was we put the board in the server, but then ran all the network traffic through that board. So you can see up there that the CPUs might generate a network request. It goes into the network interface card, or NIC, goes over a little jumper cable there to the FPGA chip, and then out to the data center network. And so the FPGA is basically the front door to the server. All into the server and out of the server interactions come through this. This allows us to actually process the network flows at line rate. And we can process the storage flows at line rate. And then we can use it for applications. So it took us 3 tries to get this architecture right. We built hardware once. The company said no. We built it again. The company said no. We built it a 3rd time. Everyone was kind of a bad weekend, and dust ourselves off and try again. And so the company decided to take this to scale. In this case, the question was, what's the difference between success and failure? For us, success was the company takes it to production and actually deploys it at scale in a data center.
But what were the objections to versions 1 and 2?
Yeah, I'll give you the quick version.
High level.
Yeah, the first version we built had 6 FPGAs on it. And the idea is we'd put it in one special server in a rack of servers, and then all the servers in that rack would talk to it. And the company hated it because it consumed a lot of network bandwidth. It was a single point of failure, and you had no elasticity. If you needed more than 6 FPGAs, you were sunk. If you needed fewer, you were wasting capacity. The second version, we put one FPGA board in every server, but then wired them up with a custom network. And so they could talk to each other, but you couldn't actually process the network traffic, the generic network traffic. And the company didn't want that second network. The Bing, who we did the pilot with for the 2nd generation, really liked it and wanted to go to production. And then at the time, there was a mandate to converge the Bing and the Azure architectures. And the Azure people said, no, we don't want that second network. So we got the win, and then it was whisked away for very good business reasons. And then that architecture that I showed you here, the successful one, actually allowed us to do everything we were doing with the other 2 architectures and more. And that was enough for Azure to take it. And so what Azure ended up doing with this design is to use it for something called their Smart NIC. And effectively, if you think back to that temporal computing, instructions flowing through data, and then structured computing, data flowing through a structure or instructions, that loosely, those of you in the systems community, that translates into control plane and data plane. And so what Azure said is, hey, we can use this for our data plane, meaning when we do software-defined networking, you rewrite the networking flows based on networking policies that you have in your data center. Like, is this person renting a virtual machine allowed to send traffic to this other virtual machine? Or is that a security attack? Like, if you're renting a bunch of servers in the cloud with a virtual private network, there's only certain servers you're allowed to send traffic to. And so what they were doing is that the CPUs would go and analyze those packets and rewrite them to enforce the policies. We move that onto the FPGA. And so now all the network flows, the packet headers get decapsulated, inspected, and then they regenerate the headers based on rules. And that's allowed them to basically run at line rate with very little load on the CPU because it's the right model. And so this ended up giving them an incredibly fast network. It's still the fastest network in the cloud. It took their latency down from hundreds of microseconds to 20 to 25 to get a packet from one server to another with all the security policy and enforcement. But for Bing and for machine learning and all these other things, the system acceleration, storage, networking, security, that's all really great. It's important for our cloud business. One of the things that we started the project for was to do more interesting big compute, machine learning, internet search, all of that. And so really the question is, what does this architecture do for applications, and how can I leverage it to do more interesting speed up in the cloud? And so I've shown you another view there where you've got the server, the network interface card, and the FPGA, all in line with the FPGA being the interface to the cloud network, which is showed up there with those higher 3 rows of boxes, the top of rack switch, the cluster spine, the cluster switch, and the spine. And it turns out that the FPGAs, because they're programmable, we can put on the logic to generate their own network packets and receive their own network packets off of the Ethernet network. And within a rack, it's about 1.5 microseconds from one chip to another. And then across a cluster, which is a few thousand machines, it's about 4 to 5 microseconds. And then across the spine, which is maybe 100,000 servers, it's about 9 microseconds. What this effectively then gives you, if you view it this way, is a structured computing supercomputer that's sort of been jammed into the middle of the traditional CPU software and the data center network. And so it's really a whole new class of computer, which we're now running at scale worldwide. And if you just look at for those of you in the HPC space, if you just look at the levels of performance, the FPGAs have been getting more and more performant each year. The chips that we're moving to this year, late in 2018, are actually capable of doing 10 teraflops per chip. And if you deploy 1 million of them worldwide, which is sort of on the scale we deploy new servers, that's 10 exaflops of compute, single precision, mind you, but still 10 exaflops, just on that programmable hardware fabric. It's in addition to all of the CPU servers. And so this is an example of how the scale of the cloud is able to bring new capabilities that I think are ahead of where a lot of the more conventional technologies are vectored. Now, how do you manage this fabric? So we published a paper in the Symposium on Microarchitecture 2016. And this is just another view of what I showed you. You've got the CPUs in the bottom. They each go up to that programmable hardware plane and then up to routers. So they have to go through the programmable hardware plane. But Azure uses this for networking and storage acceleration. But when we're in in servers running services like Bing, we just treat this as its own independent fabric, and then we schedule it independently. So we have a resource manager, so each server will donate its local FPGA to a global pool if it wants. They all do, because they're told to. They donate it to the local pool, the global pool, and then a manager keeps track of all the available FPGAs. And so I can say, hey, I want to run some machine learning application. One instance of this application I want to run accelerated needs 5 FPGAs, connected like so in some topology. We'll call that a component. And then you can go and say, hey, I want 1,000 of those 5 FPGA components. And so the resource manager will go out on the fabric, grab 5,000 FPGAs, configure them into that 1,000 components, and then hand you back 1,000 handles. So you have the IP address or the network address of each of those components, and then you can start sending requests to them. And so this actually works incredibly well because you can rate match the size of a pool to the demand from the servers that are using it. And so if you want to roll out a more expensive model that need more FPGAs, you increase the size of the pool for the same number of servers. So it allows you you might need fewer FPGAs than you have servers because they're very fast, or more because you're running a big model. And then so at scale, this becomes something we call a configurable cloud. This is obviously a logical diagram and doesn't represent the physical topology of the data center. But you have a CPU layer running traditional software. Then on the next layer, connecting through the network, you've got this structured compute layer or programmable hardware. And then the converged network. And so we're running this at very large scale, and we use it for all sorts of things. Now, I have a section on machine learning, and I've got too much material here. So and what I'll do is maybe introduce the concept and then show how we're using it, and then I'll wrap up. Okay, so I think this deep learning thing is crazy hot right now, and there's a zillion startups building hardware for it. And really what's driving this explosion in new types of hardware is that the CPUs aren't able to meet the demand. As you saw on one of the first charts, they've sort of flatlined in performance. I mean, they're getting a little bit better, but the demands of deep learning are going like this. And so GPUs and these FPGAs, and people are building lots of custom chips now to accelerate the deep learning workloads. And they're linear algebra, basically, low precision linear algebra with some other stuff mixed in. And so one of the reasons there's so much activity in this space is this seems to be very general, and we're using it for all sorts of interesting stuff. One example that Bing has done recently is what they call multi-perspective answer. So when you ask a question, we have a series of very large deep networks now running in production that have mined the web and, in some sense, mined the semantics of the language, and then you can match them to questions. And so when you ask an answer, it will give you a balanced perspective if there's not a consensus. So if there's a fact, i.e. in what year was Queen Elizabeth born, that's easy to scrape off a website, and you just need to make sure there's enough of them that agree that you don't get the wrong answer if some website got it wrong. But if you ask it a question with nuance, like,
was there a collusion?
Was there collusion? My guess would be that's not terribly nuanced, but maybe that's, time will tell. So the network will actually give you a balanced answer with the pros and cons. And doing that at web scale is actually really hard and takes very large networks. So it's an example of how we're starting to move into semantics.
Did it decide fake news, go through, and when people put stuff on, let's say Facebook, stamp something as real or not real?
So the question was, do we treat that, do we filter for fake news?
Could you?
Could you? I'm not sure that this particular model would be good for that, because what it does is it looks for groupings of consensus, and then if there's two strong sort of formed consensuses, then it will try to synthesize a balanced answer for you. But if one of those consensus that it sees is obviously wrong but widely disseminated, it'll probably pick that up, right? And I think we need the machine learning algorithms are dumb, right? They're classifiers, and so it's really easy to trick them if you feed them incorrect data. And that's why I think human curation is really important. So if you have a set of verified facts or a source of truth and you can mark it as such, then you can prioritize that in the algorithms and have that propagate through. Okay, but these things are they're just looking at big data and pulling out correlations. They're not smart in any sense of the word.
Pick up Trump lives.
Well, it'll pick up anything for which it sees commonality, right? And so if you have a large number of sites saying this person is telling the truth and a large person's percentage of sites saying this person lies, it might give you a balanced answer saying some people believe that it's like the mainstream media, right? Some people believe this, some people believe this. We're not going to take a position. Okay, and then these things have been shown, they're very powerful. So how do we use this configurable cloud? We built a system called Brainwave where we announced it at Hot Chips this year. And what we do is we take the FPGAs and we take a deep learning model and we slice the deep learning model up into chunks. Each of those chunks is just big enough to fit on one FPGA chip. So as we go to newer FPGA chips that have more capacity, we can slice a given model into fewer chunks and fewer FPGAs. And since we have all of these things sitting on the network on that schedulable fabric, that configurable cloud, we can take a deep learn model, allocate as many FPGAs as we need to pin that model in the on-chip memories. For the next gen, each of those on-chip, the memories on one of those chips provides an aggregate bandwidth of about 20 terabytes per second. So if you can stay on chip, you do really, really well. And then you want to try to send just the activations from one layer to another across the network. This allows you to lay out the network on this fabric. And so you can actually run really large models and run them super fast. And I'm going to skip ahead a little bit here. Let me make one more comment for those who are working near the space. One of the fun things about this area right now specialized hardware for deep learning, is that there's a whole bunch of different architectural paradigms that we used to argue about in the 80s and 90s, which, I mean, we sort of, the debate was settled largely with GPUs for graphics and fine-grained SIMD parallel processing and CPUs for everything else. But that debate's being opened up again for deep learning, and the answers may be different. So we have a single-threaded vector out-of-order model. There's a company called GraphCore that does thousands of little statically scheduled cores where the compiler knows everything and generates the schedule at compile time. Statically scheduled BIMD. Google's TPU uses systolic arrays, sort of IE or with the intellectual underpinnings being CMU's work in the 70s and 80s. And then GPUs, of course, use massive numbers of a massively multi-threaded model. So all of this is up for grabs. No one knows what the right answer is going to be. It's really, really interesting. All right, so let me jump a little bit ahead here. Not that yet. And so I'm just showing you a diagram here of, when you have this configurable cloud and you have these chips connected directly to the network at very large scale, you can take a model, say in green, and allocate enough and pin those. And the blue model's pinned. And so you just start pinning models. And one of my dreams and what we're trying to drive towards is getting a large number of really smart models and being able to connect them together, for different types of data and training on the fly. So that you deploy these really large models, you just keep pumping in new data and they get smarter and smarter. And then they can talk to each other to synthesize different types of data, speech and images and voice and knowledge and whatnot. And then on these chips, what we're seeing is the performance climb. So the brainwave system in particular, because we pin the data, and sorry for those of you that aren't familiar with the lingo, we don't do any batching. So you just send a request, and rather than grouping a lot of requests together to jam your throughput up, we just take one request, hit the server, it sends the response, and we've already demonstrated about 40 teraflops of performance on a custom data type called 9-bit floating point. We demonstrated that in August on the new Stratix 10 FPGA hardware, and we're confident we're going to scale up to somewhere between 70 and 90 teraflops on a single chip, by the first quarter of 2019, with no batching at all. So for those of you in the field, that's actually a pretty big deal, and it puts us in a performance lead for DNNs, for serving DNNs, not necessarily training. Okay, so I talked about structured computing as a general thing, and this is very early thinking, but what I think we're starting to evolve towards is something that for that data plane processing, when you want to fix the compute and run data through it, what people used to call streaming, and it's still a valid term, except without instructions, there's a more general, I think, spectrum of architectures that should capture that. And the control plane stuff, you still want a traditional design. But even then, I think you can do things to improve energy past the end of Moore's law. So right now, for both temporal and some data parallel workloads, we use CPUs. Of course, we're increasingly using GPUs and these DNN processors. But we've really been tied to this instruction model for a long time. I mean, von Neumann invented it. It's been incredibly powerful. But these instructions, as I said, use a lot of energy. And they are they're very fine grained. And now that we have a lot of silicon area, we can start mapping bigger structures down. And so I think what I'm hoping to move towards is something where, even for the CPUs, we start building structures of interrelated instructions. This is some of my old work from UT, which I still think is really exciting. And we're showing energy and performance gains by doing this. So I can map small structures, maybe 30 instructions at the finest grain. And then, of course, you can take these structures or larger ones and pin those down, and they just stay recurrent during a loop. And so you're not moving instructions around the silicon. As you go across, then you can pin something and start streaming data through it. Then you get to what's called a coarse grain reconfigurable array, which is a network of arithmetic math units that you schedule code on top of. Again, pin and stream. That's at the next granularity out. And at the finest grain, you have an FPGA that does kind of bit by bit, very, very fine grain arbitrary logic. But you're taking very large structures, in fact, whole programs, synthesizing them and pinning them down and streaming data through. So I think post Moore's law, I think there is a spectrum of architectures that looks very different and starts moving us away from traditional von Neumann instructions And we actually have a number of data points internally showing that this works well. We don't have them all, and we don't have automatic software on top. But if we get there, but we're making a lot of progress, and if we get there, it'll be a big shift in how we map computation to silicon for the next 10 or 20 years. Okay, that's it. Thank you very much.
Time for a couple of questions. You can ask, shut up, while I get the microphone.
Even in the current architecture, does it make sense that the thing at the bottom is still x86?
The thing at the bottom, which bottom?
You have all this FPGA, but at the end, the servers, you're still running, I'm assuming, x86.
Okay, so the question is it still x86? Let me make two comments about that.
And one is that also because of verticalization, you are such a big customer that you either ask Intel for your own custom chip, or you can design your own custom CPU.
Well, I'm not going to comment on that last question about designing our own custom CPU. We have a great partnership with Intel.
Not necessarily you. Could a theoretical cloud provider with large enough volume decide to replace the x86 with a custom CPU?
I don't think I'll comment on that one either. Let me say two things. So number one, I think that we do have some insight in how to build more efficient, even CPU architectures. So I think long term, we're going to want to build more efficient things. I mean, Intel does a great job within their x86 interface at making their processors better and better. You know, it's a very old interface. But the second thing I'll say is that, you know, if you look at the legacy tail, like all the software we run in the data center to first order is x86, and it's not like that's a declining legacy thing. If you think of that as a legacy weight I'm carrying around, it's actually that legacy weight is growing exponentially. It doubled last year. So, you know, x86 is going to be with us for a very, very long time. The question is, how do we get more efficient simulation silicon architectures while preserving that legacy compatibility? And some workloads, like the deep learning, you know, they can be decoupled because there's no legacy base, and they can be hidden behind a service. Okay, but we're going to have x86. So does it make sense to have x86 at the bottom? Yes. Do I hope the silicon architectures get even more efficient than they are today? Yes. And I think structure or structured computing is one way we'll do that.
I have two questions. One is for the FPGA compute that you're describing. Is the bisection bandwidth of your network a limiting factor at all? Because my understanding of data center networks is that they're nowhere near full bisection bandwidth.
So the first question was, are we limited by network bandwidth? And the answer is in some cases yes, in other cases no. So you have full bisection bandwidth within a rack. And then typically, as you go to higher levels, you have more oversubscription. And so you need to do spatial placement to think about those flows. And it really just depends on the rate of your service. Like these are now 50 gigabit networks moving to 100 gigabit. So within one link, that's actually a lot of bandwidth, even if it's oversubscribed. But you can, for example, I can pack a rack full of FPGAs, and then someone across the data center that has to go to the very top of the switch is going to be network bound, you know, can't drive all those FPGAs to full utilization. So yes, there are cases where you're oversubscribed, but you want to do job placement to minimize that from happening.
The second question was about the idea of pin loops, the kind of thing you might do in the TRIPS architecture.
Right.
So what sort of scale do you think is practical today in terms of like the size of a loop nest or something that could be pinned, say, in an FPGA like the ones that you were talking about?
Well, for something TRIPS-like, I think it's probably practical to pin a couple thousand instructions, which actually gives you quite a bit. For the FPGA, I mean, I didn't talk about this part, but when we first ported the back end of Bing to that first generation, the failure, we took about 30,000 lines of C++ and rewrote it to map to those 6 FPGAs. So that was 3 engineers in about a year of hard work. That's why we were sad when they didn't take the first one. Yeah.
Question over here.
Yeah, I have a quick question. So for the DIM storage kind of thing, so like I know there's high mutation rate at the rate around 10 to the minus 9, and the sequencing error is also very high. So how do you counter those problems?
So that's not my program. I was pleased to get the slides from Karen Strauss. They are doing pretty aggressive error correction. And I think they believe that they can recover, and they've demonstrated that they can recover data without a lot of loss. I don't know if they were at 0 bits. It was an image. I'd have to ask Karen for the details.
Okay, so you mean that they are able to reduce the error to a very low level so that it's acceptable, right?
They're taking it pretty seriously, and if they didn't think, I'm sure that if they didn't think they could get the error rate down to acceptable levels, they wouldn't be doing it. So if you want to send me email, I'd be happy to connect you to get a precise answer to your question.
So can you comment on how often the FPGA in the smart NIC deployed in the Azure data centers updated? Like daily, weekly?
So how often is the smart NIC updated? I don't actually know. I do know because with the current architecture, we have to drop, when we reconfigure the FPGA, you're reconfiguring the whole thing so it has to drop off the network. And the hope is that in future instantiations, we can reconfigure the application without nailing the PCIe transceivers. So when you drop off the network, you're obviously affecting your customer virtual machines. So we try to do that very irregularly. I know that the team, and one of the great things about having programmable hardware is that you can actually iterate pretty quickly. And so I know that they are generating new features monthly. So they're on a very rapid innovation cadence. But I don't actually know whether they're rolling out those new features quarterly or every 6 months. It's not daily. It's not weekly.
But there's strong incentive locked with ASIC, right? Because you do upgrade.
Yes. No, they're iterating on features very fast. And in fact, in the brainwave architecture, if we see something really interesting get published, we can pull it in a few weeks. And so we're also constantly evolving the platform. And our performance has actually been going up and up and up as we learn more.
So I'll ask the last question.
Sure.
The Exascale project, from the DOE Exascale project, we just had a big group in town last week from DOE and had conversations with them. Is Microsoft involved at some level? Do you think FPGAs will be involved in those architectures moving forward? Do you have some speculation, some ideas?
So the question, to repeat the question, is Microsoft involved in Exascale, and can the FPGA fabric play a role? I don't know that we're involved. I would suspect not, but it's possible that there's a group that's involved. I certainly haven't heard that. For the FPGAs, I think it's a very different kind of computing fabric. So I know there has been work, and in fact, Andrew Putnam, who was one of the key originators on Catapult, did his Ph.D. thesis on mapping Fortran applications down onto FPGAs. It was a beautiful piece of work, pretty challenging. I don't know if we could really get the dusty DEC codes or even modern HPC workloads to map well to this. I do know that if you look at the trends towards specialized computing, where people are going to get more performance in the future is from stuff like this and not from more parallel CPUs being farmed out. So I also think the economics of the cloud are such that HPC will move into the cloud eventually. I know it's already started, but it's just that the HPC market for us is pretty small, and so so I don't know if the stuff they're doing now will map to the FPGAs, but I'm pretty sure they'll be running on these servers in some form, before too long.
Please join me in thanking Dr.
Okay, thank you.
Please join us for a reception outside. Doug will be around.